morning. Today we have Hugo Larochelle, who is an adjunct professor here at Mila and also leading the Google Brain team in Montreal. And he will give us a talk about the progress and challenges in future learning with meta.
Cool, thank you, everyone. Thanks for coming. Where am I supposed to? Well, I see there's a camera, so it's fine. Yeah.
Yeah.
Okay.
From here to later.
Yeah. Okay. All right. Cool. So I guess what I thought I would do is it's more like a tutorial, I guess, of sorts on meta learning. And in fact, last time I gave a version of this talk, I essentially went over. I went really quick on the last part. I might turn this into a two-parter if people will have me. Like maybe I'll come back and give the last part, which is more forward-looking and perhaps thinking a bit more about things that go beyond two-shot.
You're in for the second.
Yeah. Okay. All right. So then.
Let's do the first part.
So please feel free to ask questions. I'm happy to make this less formal and have people sort of share their thoughts and really ask questions and make the most out of the next hour. And a lot of this is going over literature and a lot of it not my own even, just to give you a sense of what has been done in few-shot learning and meta learning in the past 2 years or so. So hopefully, from this you can kind of perhaps build on these ideas and get ideas for future research for yourself. So I came to start working on this topic because, generally speaking, when I once started being a faculty at Sherbrooke, my broad research agenda was based on this assumption that and this observation that in deep learning we've had all the success because we have a lot of training data, and that's had impact in many industries, applications, and so on. But of course, it requires collecting all of that data, and the assumption here is that that's not going to be sufficient for us to really reach AI capabilities for all the different problems we'd like to use machine learning to solve. Collecting millions of examples for each individual ability that a system should have is not much more reasonable than, say, when we were thinking of expert systems many years ago, and we would just try to dump as much expert knowledge into a machine for every single ability we want to solve. So, and also the fact is that scientifically speaking, we do learn way faster than our current, machine learning based system. But there's also this kind of gap, scientifically speaking, we don't understand, and in our ability to learn fast and the ability of machines to learn much more slowly. And so various approaches for trying to address this particular sort of being more sample efficient and learning new things faster. Different approaches that people like myself and others have looked at is essentially looking at other sources of data for doing some sort of transfer to a new task. Either you'd use unlabeled data, so doing unsupervised learning to learn a representation, or do some form of semi-supervised learning. You might look at multimodal data, thinking that if you have an additional modality, so if you're learning on images, but you have some text, maybe the text provides some sort of weak labels indirectly about what you actually want to learn and the prediction you want to make. Or you can try to do multi-domain data, so you leverage data that's available for certain tasks that are somewhat similar to the one you want to solve. So that relates to domain adaptation and in general to transfer learning. And that's really in this particular approach that few-shot learning and the meta learning approaches that I'll talk about fall into today. The one problem to keep in mind for this whole presentation is essentially illustrated here. What we are trying to do is we would like to solve a problem where the training set actually corresponds to very, very few examples per class. And we'll just focus on classification, and we'll focus on image classification, largely because we actually know that we're ourselves really good at doing that, at understanding an object category from a few examples, visual examples. So in this case, I have 5 classes, and only one example per class. This Sunday here, that thing, the dog here, the lion, and some bowls. And then the task is, from this training set that's small, how can I infer the label of, can I classify the image of this lion here and this bowl successfully?
So you're assuming that the test examples are drawn from one of the categories shown in the training.
Yeah, so that's the setting where we're considering. It's one where someone has provided us some labels from some classes, and that person wants a system that will later on classify other examples from that system. So yeah, part of the reason that I find this interesting, outside of the fact that I think in terms of applications, this would be very valuable, is that people are good at it. So there's also scientifically like something that we don't quite understand. That's a gap between the way we learn and the way machines learn. So this is an example that Josh Tenenbaum often gives. You know, it's hard to give these examples of new objects and give that talk multiple times, because then you've seen that the whole time, and you know, presumably you look for that object on the web after. But you know, most people, if they see the subject of this segue-like thing, then they'll be able to identify what is the other segue in images here. And we've seen pretty good progress also on simpler problems using ideas like transfer learning and meta learning. So this is also from Josh Tenenbaum's group, where they published in Nature a method that was able to classify characters from new alphabets. And it was doing this by transferring this ability of doing that was trained on a set of training alphabets. And they were reaching, you know, the performance of so one sort of concrete illustration of how people could use this, and the type of problem I have in mind when I think of why am I, you know, trying to solve, you know, get better performance on this few-shot learning data set, would be one where you really have someone interacting with a machine, providing their data for some classifier they want to train, and being able to do this without the intervention of a machine learning expert. So one example I often give is this sort of little activity I did with my kids, where we'll train a classifier from my webcam camera. This is on the Teaching Machines website. This is an experiment with Google where you can sort of play with various experiments they put and design in the browser. So this is one about kind of teaching about, you know, what it is to collect data and then how that impacts the classifier. But what we'd like to do, for instance, is to be able to train a tree-class classifier from simple images we would take. So in this case, I'll just start the video, hopefully. There you go. Okay, so I go on my webcam, and then I'll do a classifier where it's either detecting if I'm smiling, if I'm yawning, or if I'm scared. It's the best scared I could do. And I collected images by pushing on the corresponding button, and you can see when I make once I collected my data, it gets the problem correctly. But what you want is to generalize. If I ask my older daughter to try it out initially, so if she smiles, it always keeps predicting the last class, which is scared. Okay. So then what you'd like is for anyone to be able to kind of collect the data themselves. So in this case, you know, collect images of her smiling, of her yawning, and of her being scared. And then, you know, hopefully then after that, it works. It works for her. And we'd like to want to be able to do this without the intervention of a machine learning person. You know, it should collect data and it adapts immediately so that their other sister comes in, then hopefully it works. In this case, she smiles and then it's green, purple when she yawns, and so it was able to generalize from a few examples. In this example, there are a few reasons why, you know, it worked. First of all, we tried a bunch of other tree classification problems. A lot of them weren't working, so this was the one that actually like ended up producing this demo from a few examples. But the fact is, most of the times, it requires many more examples. Also, the generalization here that's asked is a bit easier. You know, they are sisters, so they're supposed to share half of my genes. Supposed to share half of my genes. But of course, the type of generalization that we would expect, like here, the background is not really changing. So if you were to take this and then go in another setting with a different background, most likely it would, you know, possibly break. But if we had something that could just work that easily, that anyone could collect images with their camera and they could get a visual classifier, you could imagine this being very useful. And then if you could do this for more than just image classification, again, I think this could have a lot of impact. All right. So that's kind of what we're after and the type of problems that we think we could solve if we were better at few-shot learning. So few-shot learning is this problem where we assume that for any new given problem, we have a small training set. That's really what makes a few-shot learning a problem. And people have thought a lot about how to address this particular setting in the past, and I'll go over sort of older literature on the topic. One approach that more recently has started being making progress and going beyond what people have done before is the idea that when we're doing few-shot learning, really what we want is a learning algorithm noting A that produces a model, we'll say the parameters of some model M. When it's fed as input, when the algorithm is fed as input this training set, we want a learning algorithm that produces good parameters, that generalizes well to new examples. And the approach we'll take in meta learning is we'll treat A as a model that we'll train. Okay, so we will learn the learning algorithm. That's why we call that meta learning. So before I go into the various approaches for this, sort of talking about related work in that space. Actually, transfer learning, there's been a lot of success already, in particular in vision and images. We all know that a lot of times, if you pre-train a model on ImageNet, that will give you a good embedding, good representation that transfers pretty well to other tasks, and sometimes surprisingly different tasks, like for cases of things like medical imaging tasks and so on. But often what this requires is you do the pre-training, or you take some, you download some model that's been pre-trained already, and then you use that as the pre-training, but you still do a fair amount of work, like, potentially tuning the hyperparameters of the learning rate and things like this. In a sense, what we'd like to do here with many of these few-shot learning methods is that we don't want to have all of this legwork that happens after, where you just take the initialization, but you still need to do things like tweak the model, the learning rates, some amount of regularization, and so on and so forth. We would like that to be as black box as possible, and that whole process of transferring to a new data set to be effectively learned. There's also been, yes?
But the meta-learning is also doing the transfer, the multitask training, what to share between all these.
Yes, that's right. Yeah. So we'll do a form of, it is, especially the stuff that I'm talking about here, it is doing a form of transfer. But I think what we're after is that once we've done with the meta learning, there's no like post sort of tuning of learning rates and things like that. It should just be a black box someone can. Whereas right now, the way we do transfer learning is we download this model, but there's still a machine learning, expert or scientist that is tuning the learning rates for it and so on and so forth. And also, while transfer learning sort of works, often really the success you get is still quite dependent on having a lot of data for the target task. So there's a lot of literature also on one-shot learning, which is this extreme case of few-shot learning. We have just one example. So some of these papers actually, even though they label themselves as being one-shot learning, they sometimes present experiments where they vary the number of examples they have for a new task. A lot of that literature actually was, pre sort of deep learning revolution, where people were using hand design features for representing images. And so in a sense, what we're trying to do here is we're kind of revisiting that problem, but we're kind of leveraging the success we had with end-to-end learning of, in this case, both the features. So we'll end-to-end learn the feature representation that's useful for transfer learning. And also, we want to end-to-end learn the whole process of doing that adaptation as well, as opposed to sort of defining, say, some graphical models that does the transfer learning in some way. We want to actually end-to-end learn it. All right. So a few definitions. First, what is a learning algorithm? Since that's the thing that we'll be learning, it makes sense to define that and make sure we're on the we all agree on what we mean by a learning algorithm. The learning algorithm is an algorithm that takes as input a training set. So some examples, X and Y's, where X is the input image and Y would be the class label. And it outputs either a model or, say, the parameters of some model, which I'll sometimes refer to as the learner. And what we think of a learning algorithm as being a good algorithm is one where the performance of that model that's produced by the learning algorithm is good on some new example, some test set, okay, that is different from the training set. That's what the learning algorithm is. So a meta-learning algorithm will be as follows. It will, because it's a learning algorithm, it also takes a training set, but in our setting, it's going to be a meta training set. It's a meta training set because that training set will correspond to many training test sets. So often these pairs of training and test sets will refer to these as an episode. And our meta-learning algorithm is also going to output parameters, but the parameters it outputs conceptually are the parameters of a learning algorithm itself. That is an algorithm A that can take in a training set and then produce a model that can be evaluated on the test set for some episode. And again, in meta-learning, we're interested, like a good meta-learning algorithm is one that will generalize to a meta-test set. Okay. And this meta-test set, well, it also has episodes as part of it. That is, other splits of a training set and the corresponding test set. And that's where we evaluate our performance. All right? Is that clear? If there are questions about this, and they're usually on. Please don't hesitate and ask.
So the output of the meta-learning algorithm or the parameter of the learning algorithm.
Yeah, that's right.
That's what you mean by
yes.
Parameters theta.
Yeah, this is meant to be a theta that's different from bold theta or capital theta. But that's right. Yes, conceptually, that's how we think of meta learning. How we do it. Any other questions? And I want to emphasize that this notion here of we evaluate the performance on a meta test set. This meta test set should be different problems, different problems from what you've seen at training time. I think you can, yes. That's a good question. So it depends on which meta-learning algorithm we'll use. So some meta-learning algorithms assumes a particular form for what the learner will look like, how it's parameterized. So for instance, if you think of it as, let's say, if you're familiar with MAML, which is essentially this approach where we backdrop for gradient descent. In MAML, you learn the initialization and maybe parameters of the gradient descent procedure, and those would be the parameters of the meta-learner. But then MAML, when you feed it a training set of an episode, it produces parameters of, say, a CompNet. And those would be the parameters of the learner. The learner would be the CompNet, and MAML, the meta-learning algorithm, learns an initialization and potentially learning rates to use at different time steps. That's where the distinction happens. Sometimes that distinction is not as clear-cut. And so that's why this, in the context of a gradient-based meta-learner, that separation is easier. But there's some learners that really don't draw a clear distinction between what the learner is and what the meta-learning algorithm is. All right. So the point I want to make is that I think sometimes we refer to various things as being meta-learning. From my perspective, if we're doing meta-learning, that we are interested in learning algorithms, and we are interested in generalization. So say if you're doing hyperparameter search, and you're defining one that works well for CFAR10, but you never actually look at, there's nothing in the parameters in the parameter search procedure or the hyperparameter architecture search procedure that's being learned, and there's no evaluation on how this trained, architecture search procedure generalizes to new problems. Then, as far as I'm concerned, that's not really meta learning. It's you're designing an optimizer perhaps for a particular problem, but you're not looking at generalization to new problems. And to me, that's like a key for something to be meta learning. I think various people will have their own perspectives as to what makes a meta-learning algorithm a proper meta-learning algorithm. Mine is probably, I've seen people being pretty restrictive as to what they define as meta-learning. That, to me, as long as you're learning a procedure that takes a training set and produces a model that can make prediction on some new examples, and that you're evaluating on problems it's never seen before, then I think technically speaking, that's a meta-learning procedure.
So the definition you gave before wasn't a minimal set then, because you're go back.
Yeah.
The D meta test could be essentially like the D prime train could be empty then in that case. The case you just described.
D prime train could be empty.
Yeah. Like you're just doing generalization to some other test, some other domain or some other distribution.
I guess here I didn't write it explicitly, but D meta train and D meta test should be different.
No, yeah, but let's assume they're different. The question is do you require training in this new domain for it to be meta learning?
So there's no adjustment of the learning algorithm itself on the test set, on the meta test set. It is fixed, and then you
training the base learner, say, training the little theta.
This will be a function of D prime train.
Right.
So it changes for each episode. For each episode in the meta test set, it will change.
I guess what I'm asking is, do you consider zero-shot transfer to a new domain as being meta learning?
So definitely not. It's not quite few-shot learning in the sense that we kind of assume here that the training examples are examples. Zero-shot learning is even harder, where you actually have a description of the task. So it doesn't fit that description. And when I look at a few-shot learning paper, I don't expect zero-shot learning experiments necessarily. I think you could somewhat argue that if you're looking at generalizations in the descriptions, there's a sense in which it is doing meta learning. So I might be inclined to include that in the setting of like, as long as you're looking at the evaluation of new problems and new descriptions of problems you've never trained on, then I think, yeah, arguably there is a form of learning procedure that's happening, but yeah, I'm not sure. I'm not sure exactly where I fall. But I feel it's just tweaking definitions at this point, so I don't know how useful that is.
But it's a new field, and it's useful to actually have as clear.
No, sure.
Cool.
Yes.
But wouldn't zero shot be if you didn't have the meta training set, not the meta test set?
So in meta training set, I think you would have essentially like, I didn't expect to give a talk on zero shot learning. So
you wrote the paper.
Yes, some time ago. I wrote the paper on zero data learning. So I think in this case, normally in zero shot, you have training examples. We also have, for each class, you have like metadata, essentially. You have a description of the class. So here and there would be additional data, which is for each class, what's the description of it, that is not necessarily grounded explicitly in images, for instance. Like in some stuff that people do is like they use a Wikipedia article describing that object category. Yeah.
So I agree that transfer to a new distribution is the most interesting problem. But it feels to me like hyper-optimization, even from the same distribution, is meta-learning. Like you're learning how to do optimization of architecture to get better generalization, for example. It's the same distribution. So you are.
I think if you resample the training test sets,
you are learning algorithm for that distribution.
But if you're using the same training and test sets, effectively, but then you're not looking at generalization.
Normal training focuses on the training error. Meta learning allows you to focus on generalization. So for me, that's where the central distinction is.
So I guess it is true you're looking at you're optimizing the validation set error on the validation set when you're doing hyperparameter search, and then you're looking at, on new examples from these classes. But that is not really impressive.
But that's like the most common thing people do, right?
No, because distributions here are over tasks. And I would argue it's the same task. You haven't generalized across tasks. You only generalize across examples.
That's your definition. But
yeah, it's true. It's my definition. I think I prefaced this by saying, according to me.
The word meta-learning, learning to learn. I'm not sure you're restricted to that multitasking.
I guess I'll tell you why I think it's a good thing to define it this way, is that to me, it means that we're going to be more ambitious as to the problems we're going to be solving. Because, and And I'm not saying that architecture shouldn't be a problem people study. I'm just saying that confusing that with other work that is doing meta learning, that is actually looking at generalization across tasks, that to me is harder in terms of generalization. And so I think it's deserving of its own category.
What are the techniques?
Yes. I did backprop to learn hyperparameters in 1998 or something.
So yeah, but architecture search is, I mean, there's there's some similarity.
Can you give one example of what you consider to be real meta-learning, one example you consider to be kind of the same task?
Well, I think this is the one. So, yeah, so if you say,
well,
according to me, it's not. That's to me, that's hyperparameter optimization. Yeah.
You're going to talk about parameter for learning algorithm that's hyperparameter free. Because you've hidden the hyperparameter optimization inside of it. Would you consider it a meta learning algorithm?
If these are different problems, yes. So some people, for instance, have. I think there must be examples of this where they actually have trained some sort of agent that is doing architecture search. And maybe it has parameters inside it that does that process. And if then they looked at, say they trained it on CFAR 10, and then they looked at, okay, well, does it find better hyperparameters for CFAR 100? Then to me, like that at least is a form of generalization that I think is interesting. All right, so I want to go over the literature a little bit and not just my opinion. So. Or Yashua's. So, all right. So in this setting where we're doing meta learning, trying to make things more visual, our approach to doing meta learning is as follows. We want to generalize to this problem. It's an episode. It has a training set. It has a test set. And what we're assuming here is that we're going to have, and we're assuming it's part of the meta test set. And then we're also going to have a meta training set with other episodes. So other splits in training and test. And importantly, the way we usually set up, so the way we essentially make this a generalization, the way we make these test set examples different is that we don't just assume they're different images, we also assume they're from different classes. And that's how we're going to have some difference between the training and the test. So somewhat to Yashua's point, this is not IID sampling of the training and test set. The test set is coming from a different distribution from the training set. This is partly, we could do IID sampling if we had such a large set of tasks in terms of classes that IID sampling would mean there would be a substantial difference between the training and test set. But for a lot of these data sets out there, they're like, for instance, Mini ImageNet, it's a total of 100 classes. You could do the 1,000 ones, but even then you would end up probably sampling almost exactly the same set of problems in terms of classes in training and test. But the way these episodes are created is as follows. So initially, for a lot of these benchmarks, for the meta training set, we take a subset of the classes of a larger data set. So Mini ImageNet, which is one that's used a whole lot that I'll refer to often, is already a subset of 100 classes from ImageNet. From that 100 subset, 64 were put aside for generating meta training episodes. And then when we create an episode, the process we do is that we pick a random subset of 5 classes from these 64. And those are the classes that are going to use to generate one episode. And then for each class to generate the training set of the episode, we pick randomly some examples from that class for each class. In this case, I just picked one example for 5-shot classification. It would be 5 examples. And for the test set, we pick another set of randomly selected but different images from that same class. And then the meta test set in, say, Mini ImageNet is another distinct set of 20 classes from that same first set of 100 classes. So that's how we make the problems different.
So is there a guarantee about there'll be some new classes there, or?
You mean in meta test or?
Yeah.
Yeah, for sure. Because so this is 64 classes, okay? And these are other 20 that are not the 64 classes. Okay, but they come from this 100 set of classes from ImageNet. That's how we construct a meta learning benchmark from an existing data set.
Is there some reason why you're only picking 64 classes? Like, why not use like almost 1,000 and
Yeah,
you expect better
I
performance?
think this is so Oriole came up with the initial setup. I never asked him why he did this. I think it's largely so that the problem is smaller. But even though you could argue that even if more classes, I mean, you could imagine that if you have 64 classes, you're going to overfit earlier, so you're going to train not as long, and so that's like a smaller scale problem. I think that's partly the motivation.
Yeah, it's because there are too many dots in the class.
And then it would be too similar. Maybe I'm not sure. That might be true.
In the 1,000 categories, how many of them are dogs?
I think very good question. I'm not sure.
Like 300.
Yes.
It's a bit like a Nemo game. Like you look at the 5 first thing, and then you have to remember which one you saw before, and you look at your account.
But it's not just remembering which one, because there's also, you're not going to see the same image in the test set as you will in the training set. So what's the closest thing you see? And some methods explicitly are doing this, but they're meta trained in a way that they can do that successfully in an end-to-end way. Yeah.
Also meta trained. I saw some models which we trained on ImageNet and then do meta.
Oh yeah, so I mean, to me that's that's an interesting mention, and I'm gonna maybe touch on that a bit more later. But that's a trick that people use to get a better initialization of a meta learning model, and that to me is fine. That's like one trick over. It's like whatever optimizer you're using for meta learning. That's another dimension in which you should explore. So to me, that's more part of like how are you successful at training a meta learner. As long as you're showing that, you actually are improving over the initialization. Yeah, but often even meta learning algorithms that use a pre-trained model on ImageNet, and again, here you need to do pre-train on just these 64 classes and no others, because otherwise you'd be cheating. Because these 20 classes are also from ImageNet. Normally, they like say for mammal, I haven't talked about mammal yet, but I swear I will at some point. So you often use that to initialize the initialization that's trained by mammal, right? And normally also tuning that is important. So don't keep that fixed. So to me, the short answer is if you're using a pre-trained model and regular, say, 64-way classification to initialize, you're effectively trying to address what we don't quite understand, which it seems like training some of the meta learning algorithms is difficult somehow. And using these initializations that are based on the same data seems to somehow improve the performance. Yes.
Then we do meta learning. The meta test classes and meta tests, are these different from the classes the ImageNet, or because if you
No, they're also from the subset of ImageNet.
And then
It's in so I mean if you do take a pre-trained model first, you should make sure that pre-trained model has never seen any data from these 20 classes. That's for sure, and that's what people do. Now, if the question is, isn't it cheating that they both come from the same, overarching data set? I think what it means is that it's making the generalization problem easier. It's harder than considering the same set of classes but different images, but it's definitely not. that makes predictions. And so you would sort of iterate over episodes. You can use mini batches of episodes also, but every time we usually do some form of gradient descent on the product of the meta learning. And then ultimately, we evaluate the performance on episodes on the meta test set. All right. A few words about nomenclature. So I will try to use as often as I can the following nomenclature, which is that an episode that's essentially a data point in my meta training set is a pair of a training and test set. And that means that my training set and my meta test set, they have each episodes that are pairs of training and test set. There are other papers that instead will refer to the training set in an episode as the support set, and then the test set in an episode as the query set. And that allows them to use training and test set for referring to what would otherwise be the meta training and meta test set. It makes presentations much easier and less confusing. Not as cool. So I tend to use the one on the left, largely for that reason. But you should be aware going into papers like the introduction that we like to skip sometimes. Will identify which one they're actually. And I might slip in the support set or query set accidentally. I will try to stick to the one on the right. So in terms of what is typically the loss function we use when we're evaluating the prediction of the model produced by a meta learner on the test set of an episode, often we essentially use the cross entropy loss on the class label assignments. You can kind of think of it as evaluating this loss function where you're doing a prediction over the label of some new input x prime I. And that's effectively also conditioned on the training set of that episode. Okay, so the whole meta learning procedure, you can think of it as essentially giving you a way of a model for this. What is the distribution over the label of a new example x prime? And then you're trying to minimize that average negative log probability. Okay, so trying to assign high probability to the correct class of these new examples for that problem, where effectively that information about what that problem is provided by the training set in the episode.
So the capital theta there was the output of your.
So the capital theta is effectively part of the meta learning. That's what your meta learning.
Yeah, but one thing is P of capital theta, blah, 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 as a function of P train is basically, it gives you a theta, which gives you then a
No, what is a function of D train was the lowercase theta. And the capital theta, that's the procedure that takes in the training set and produces the model. All right. So in the time that I've left, I will hopefully cover all of this. So I like to think, so effectively once we've defined how, the way we approach meta learning, this episodic framework where we're doing graded descent over episodes. Then what's left is how do we parameterize learning algorithms? So that's kind of the model aspect of it. We can think of various ways of defining a learning algorithm that we can backpropagate into. And I like to think of it there being like two types. So again, like most things, it's hard to put a strong threshold between various categories, but I like to think of it as there being two types of approaches. There's one where we will parameterize our learning algorithm by taking inspiration from a known learning algorithm. And we will just take that learning algorithm and we'll introduce new parameters maybe in it, or some existing parameters will become trainable. And what I'll go over is, for instance, matching networks, which you can think of as taking inspiration from a k-nearest neighbor learning algorithm or a kernel machine. If you're using a Gaussian classifier, you take inspiration from that. A Gaussian classifier in some embedding space, that's effectively a prototypical network. If you want to think of using gradient descent and then backpropagating through gradient descent, approaches like my clear work on meta learner LSTM and MAML also is effectively leveraging that modeling approach. That's one way. And the other approach is just, give up on all of our inspiration or all of the prior art on learning algorithms and just be like, let's throw a neural network at it that we know can take as input a set and can make predictions on new examples. Doesn't matter if it's close or not to a learning algorithm, we'll just define a TensorFlow graph effectively that takes in a training set and can make prediction on a new test example. And it's train it to become a learning algorithm, to make new predictions successfully on new examples. And the examples of that are man and cell, which I'll talk about. All right, so let's talk about the first category. We'll take inspiration of a known learning algorithm. The first one, which is one of the early papers that in particular proposed the medium internet benchmark, which people use a lot now. It's effectively training a learning algorithm that does pattern matching. That is, what it does is that it will take the training set here, it will have an embedding function that produces a particular representation of each of these examples. We also have a potentially different embedding function that takes in a test example in the episode. These will be compared with some distance function, and that distance function will determine a weight. So this is the ultimately with that distance function, we will obtain a normalized weight over that effectively determines how each training example in the training set will vote and the weight of its vote towards its own class assignment for this test example x hat. Okay, and the way this was characterized is that we have two different functions for the test, embedding the test example and embedding the training example in the episode, and then we just take some similarity function, pass that through a softmax, and that's how we obtain these weights. So if you think of the labels yi as being a one-hot vector, you're essentially just averaging with some weights determined by these terms here. You're averaging one-hot vectors, which will give you a distribution over labels. And that becomes your P of y for the test example. And then in the paper, they consider doing things like just having the same embedding function for both G and F and sort of separately embedding each example either on the training set or the test set, and then using that. But it also looked at, and they got better results on medium ImageNet by having some more complicated a recurrent neural net that would actually take in the full set, put it in some arbitrary order, and then just go left and right to get a sort of task-specific representation in a sort of more generic way. I won't go over the details of these architectures. You can look them up there. But essentially, the short story is they kind of take this kernel machine-like equation, they throw in neural nets at it, and they train those neural nets to make good predictions on the test set given the training set.
So it's kind of tough, at least for me, it's a little tough to see this as like learning to learn, right? Mm-hmm. It's more like you're learning to solve this task, which is kind of kind of a one-shot task. I kind of view this more as like a task description, like this test sample is going to be one of these things, right? So it's just more of a comment. It's a little tough to see this as meta learning.
It's to me, it sounds like kind of saying that KNN is not a learning algorithm, really.
Yeah, it's kind of like saying that.
I mean, that's somewhat debatable.
Yeah.
I'm going to build on most people's understanding of KNN as a learning algorithm.
Basically, just learning a good representation that works across the task.
A lot of what it's doing is that, yes. But it's not. The reason why it's not just a representation in their paper, they don't have the representation in the sense of like it's an embedding they apply uniformly to all examples. They have looked at creating a representation for each example, taking into account that it's a set and that there's something encoded in all of these examples together as well. So it is embracing the notion that A is a set.
So G is applied for each.
No, there's one version which is bidirectional recurrent neural net, and that's the one that works best on medium ImageNet.
In that sense, it's really learning an algorithm.
That's right. Yes.
I think to answer Aaron's point, is just that KNN is basically the simplest learning algorithm where you don't think it's learning.
Well, there's like, if you think of like a learning phase and an evaluation. Yeah, but like
you say it's loading.
Yeah.
Loading the example.
Yeah.
So that's learning.
Yeah.
So, if we can't agree on this, then there's no point in, that will have repercussions as to what is meta learning and what isn't. So another one, which I mentioned, the prototypical network, You can effectively think of it as finding a good representation that works well for a Gaussian classifier. And it's been pretty effective. It's one of the methods out there that often has pretty solid performance, and that some don't consider meta-learning. So here what we're doing is that instead of having this pattern matcher that compares a test example in some representation space to each individual example in the training set of the episode, we're first going to extract some sort of summary of that class, which a prototype. In that paper, the way they extract the prototype is by actually taking the average of some hidden layer, essentially, some embedding space that's the output of a neural net. And that's going to be, if you do this for all examples in class K, that's going to give you the prototype CK. And then to get a distribution over the label of a new example X, you will compare the embedded test input with the corresponding prototype of each class and calculate the distance, take the negative distance to get a similarity, and pass this through a softmax. Okay, so that's like really, really simple, and that already gives pretty good performance. And the way you can think of it as meta-learning is that you're learning a representation that works well for a Gaussian classifier. It's true for a Gaussian classifier if the distance function is the squared L2 distance. But you can use other distances.
Call it Gaussian.
It's a class, well, hopefully that's what people call it. It's one where for each class you essentially train a Gaussian density model, so you compute its mean. And let's say you make the assumption, which most people do in Gaussian classifiers, that it's the same covariance matrix across classes. And no, because you compare with the mean, not each individual example. So it is not nearest neighbor.
It's Fisher discriminant.
It's what?
Fisher discriminant analysis.
Well, is it just computing the mean and then comparing with the mean? I don't think
this is simpler. There's no covariance.
Oh, I think you use the same covariance.
But yeah, no covariance.
Usually use the same covariance across classes. I mean, effectively, if you want to think of this as a Gaussian classifier, the predictive function might be similar to also Fisher discriminant analysis, because there's, in the learning algorithm, there's not just like the model itself and how it makes predictions. There's also how you train it, which we often.
It's not much different from the other one. You explicitly consider the fact that you have multiple examples of the same category and the average there.
Yes, you have this bottleneck. No matter how many examples there are, you need to summarize this all into a prototype.
But on the mini ImageNet example, set of tasks, that would collapse almost the same.
So we will do 5-shot classification, not just 1-shot. It's just easier to show just one image.
It's always like that?
People tend to do 1 and 5-shot.
Okay.
But I mean, and moving forward, we should do more. But, yeah.
I think another way to look at this too is it's like learning a similarity metric, because you're basically fixing to a very simple similarity metric.
Mm-hmm. Yeah.
Corresponds to your Gaussian. But by learning that, you're learning a projection that implements an arbitrary similarity.
So this might be true the fact that we're comparing to a prototype, I think, makes this less about, when I think of similarity metric learning, I think more of k-nearest neighbor. I think more of comparing examples with examples. Whereas the prototype here is sure living in the same dimensional space, but you're learning a representation such that prototypes and test examples are comparable.
Right, so you're learning a similarity metric not to compare points, but to
yes,
compare
that's
points to
I think you can think of it this way. All right. A few things to say about this. So, yeah, the distance function actually can be anything, but if it is the Euclidean squared, you get the Gaussian classifier. And this idea of just assuming at the top there's some learning algorithm that is doing something, like a Gaussian classifier computing averages across classes and giving you a predictive function this way. But you could replace that with any other classifier that you can backpropagate. It's just a Gaussian classifier because it's just computing averages. It's pretty simple. People have looked at assuming it's actually a least square classifier, so one that essentially treats classification as a linear regression problem. This is an if submission, for instance, here, with meta-learning with differentiable closed form solvers, where they And in general, they're making the point that if you have a closed form solver of the learning algorithm, you can backpropagate through it. So you could do something else more sophisticated than that. And that is an interesting direction. I don't know to what extent there's like a whole lot of other classifiers we could backpropagate through at this point. But
so what about not backpropagating through? Like, are people looking at reinforcement learning methods where you don't want to backpropagate?
I'm not sure. I can't think of an example right now. I mean, the answer, given how many papers are sent on archive these days, is almost yes, but I can't point you to one paper.
It's not a uniform distribution.
That's true. So I don't have one reference that I can give you.
For me, I mean, like, do you know if people tried and it didn't work?
I would be surprised if it didn't work, because I think there's a lot of value to doing like gradient descent end-to-end. Maybe if you pre-train in the regular way, it's possible that some RL-based fine-tuning would be sufficient.
I mean, one problem with backprop is if your K is large, like 1,000.
K being the number of steps.
Oh, okay. Or number of steps of
gradient descent.
Meta.
Yeah.
Well, yeah. Then for sure backprop is even going to work.
We'll talk about mammal in a few. I'm just going to say seconds, but it's going to be minutes. But I think it's worth investigating, but probably you want a good first pre-trained model, I suspect, for this to actually. What's interesting also is that in the prototypical network paper, they actually get better results by training on more ways. So if they're, in all the examples I've shown, it was always 5-way classification. So way is the number of classes, shot is the number of examples per class. In the experiments, they showed that if they train for 20-way classification, they meta train for 20-way classification, but they evaluate for 5-way classification, they tend to get better results. So, and there are other people, there's this Element AI paper also that is doing this sort of leave one out type of meta learning where they have evidence that this works better as well. And I think the reason I mentioned this is that it is not entirely clear that the way, well, so far evidence suggests that the way you do meta training does not necessarily need to reflect perfectly the way that you actually evaluate your learning algorithm. And that hints at difficulties of doing optimization potentially for these meta learning methods, and that we don't have a good understanding as to what's going on there. The other point, which is maybe my next slide, yeah. So another extension of prototypical network, another paper by Element AI appearing at NIPS this year, is extending prototypical network by making the embedding function that you apply on your examples be a function of the training set or support set of the episode. And they do this essentially using film. They take the set of support set examples, the training set, and then I think they get prototypes in the regular prototypical network way, but then they average the prototypes themselves. And there's got to be someone here who knows this more than I do. David, maybe. So correct me if I'm wrong. No, you don't? Okay.
Sorry.
Well, that's great. Then I can say whatever. So the task, so that gives you a task representation, the average of the, shit, that's right. And then you take the prototypes. The task representation is the average of the prototypes, and this is fed into a network that produces as in film, the sort of bias and multiplicative factor that will now be gating, I believe, the same embedding function. And there might be other components as well later on. And they've shown that they get better results on mini-misset by doing this, which is, again, taking a bit more into account the sort of set structure of the training set here compared to a regular prototypical network. And they also show that when they do this thing where they both train the embedding function to be useful for a regular 64-way classification and do this episodic training, that they get better results. They don't do it by just doing pre-training and then initializing these weights to just a regular meta learning procedure. Other people have done that and found that useful. In their case, actually, the paper says that that wasn't as successful as a sort of more gradual sort of mixing in regular 64-way classification and episodic-based training. So I don't know why, but so apparently there can be other better ways of sort of combining the regular type of training and embedding function and this one. All right, what else? So,
Hugo,
yes.
can you mention?
Yeah, so no, it always improves over just 64-way, and that's usually a baseline. So, and which is important. Otherwise, there's no point doing this. But yeah, normally you do get additional gains in performance. These aren't always like way better, but there is an improvement to doing that. Also, there's an interesting view of prototypical networks where if you're using the squared Euclidean distance when you're comparing prototypes and examples, you can expand that into essentially an expression which is the embedding of the test example times the prototype, because it's a squared function and you can expand the term. And then there's a bias term which is essentially the prototype times the prototype, so the squared norm of the prototype. If you think of these effectively, you can think of these as the output bias and weight for that class. If you were using the embedding as the rest of the network, it's kind of like prototypical networks are just producing the parameters of the output layer of a network with a softmax output. And other people have looked at generalizing that effectively and actually have a network producing, say, convolutional filters directly of a neural net. So this 2016 NIPS paper was doing that. Fortunately, it's developing a different set of problems, but it had some good results. And so I just want to put it out there that the one approach is to have some neural net that produces parameters, not through gradient descent or anything like that, but through some differentiable function. And there's also a relationship with graph neural networks. So some people have just thought of the training set as a essentially fully connected graph, and using graph neural networks to propagate the label information of the examples in the training set towards producing a prediction of the label for a test example that would also be part of that graph but wouldn't have its label. This was an IQ paper earlier this year, which you might want to check out. I won't go into details, but that's another, if you're doing graph neural nets, there might be interesting applications here in the subnet. All right, and then I think probably the final thing I'll touch on is the other approach for designing a meta learner, which is to take inspiration from gradient descent. So the idea here is to kind of notice that when we're doing gradient descent, which is the sort of almost universal algorithm we always use almost to fit a model to a training set, what we're doing is that we have a set of parameters, and then we're updating it using this linear equation that involves the gradient of the training set examples with respect to my current set of parameters. And that gives me the next value for the parameters for that task, and then I iterate this some number of times. So in this paper that we published at ICLR 2017, we kind of made the connection between that and what is the latent, the cell state of an LSTM, where LSTM also does these kind of additive updates of the cell state, where the cell state is multiplied by forget gates, and then you add to this a contribution to the cell state multiplied by an input gate. And if you think of if the cell state contribution was the negative gradient in some parameter space, and if the input gate was the learning rate, and if you didn't have a forget gate, then you recover the equations of gradient descent, which essentially suggests that we can unroll, like we unroll recurrent neural nets or LSTMs, we could unroll gradient descent updates and backpropagate through them. And in our case, we tried to stay as close as we could to the LSTM setting, where we have an LSTM where its cell state is as large as the number of parameters in my model. So for ImageNet, this would be a ConvNet. And then I have these input gates, and these forget gates are effectively producing a learning rate for each of the parameters. And we also kept the forget gate thinking that they might apply some form of regularization. So if it's shrinking the parameters towards zero, that's kind of like, say, weight decay. And then we can unroll this.
Don't want the n squared parameters.
That's right. But what we do is that the set of parameters that produces the learning rate and the shrinking, the forget gate for each parameter of my ConvNet, so that LSTM is the same across all parameters. So you can think of it as it's learning the same optimizer that's applied across all parameters of my ConvNet. So there's a form of parameter sharing going on effectively. Also, what we will do is that instead of using as the initial starting point of my gradient descent, we'll actually learn it. So this is like the initial cell state C0 here. So in the context of meta learning, that's theta 0. Theta 0 will be learned. So we're going to learn initialization such that after a few steps of gradient descent that is modulated by an LSTM, we're going to reach a model that has good generalization on the test set of the episode. Is there another set of people waiting? And then no? Okay. Thank goodness. So that's sort of the graph view of what I've just described. You have this LSTM, this meta learner LSTM that at an initial state, the initial parameters of my ConvNet theta 0 looks at what is my performance of the support set or the training set of my episode, produces gradients that are fed to the meta learner so that it can produce a new suggested value of the parameters of my ConvNet, my model. And then I evaluate that again on my training set, and I do this some number of times. And then ultimately I look at what is the performance of the test set of the episode. And that's the error that I backpropagate through this whole chain of this whole unrolled graph of the LSTM. Okay. A few other things that I mentioned that I haven't mentioned yet. Doing some form of preprocessing on the gradient that is fed to the LSTM has been found to be useful. You can look at the learning to learn by gradient descent paper from DeepMind, where they use a similar thing, but to actually learn an optimizer, not for few shot learning. But there are things where like going more in the log space and actually sort of separating each gradient component into two terms as such here was found helpful. Yes? Yeah.
Since you're ingesting the sequence to an RNA, aren't you imposing an order constraint now, right?
Oh yeah, that's a good point. So actually in this setting, because we're in few shot learning, what that means is that the training set is very small. So I can do full batch gradient. So I can actually calculate the gradient on the full training set. If the training set was larger, then indeed I would need to impose some sort of order. But in this setting, actually, so it's not really stochastic gradient descent. I'm unrolling regular gradient descent, batch gradient descent.
Order dependence, which need not be
dependence in?
Eating X2 after X1.
No, but what I'm saying is that X1 and Y1 is the same across all these steps in few shot learning, because I can take the full training set. Otherwise, if it was actually not so few shot learning, like 1,000 examples, then perhaps I would want to split into mini batches, and then there would be this issue. Naturally, the way I would address that is I would just shuffle the order for every update, and then you might consider actually at meta test time when you're evaluating, just apply the same procedure, so on essentially moving you forward past LSTM on a bunch of random orderings of the same mini batches, and then create an ensemble. And I wouldn't be surprised if that was better than any individual sort of order that you. And then a few months after this paper, Chelsea Finn from Berkeley proposed to essentially just scrap the LSTM. Just use actually regular gradient descent with a constant learning rate. Still learn the initialization, so that's really important. And she showed that she got like just as good results, and in fact, in that paper, a bit better. And so that's called MAML, model agnostic meta learning. I think the reason it's agnostic is that it doesn't matter whether you're you want to do meta learning, assuming the model is a ConvNet or any other type of model. As long as it has a parameterized space, you can apply MAML to meta learn it in the few shot learning setting. And also there's an improvement that's reported in this paper that's called bias transformation, where in addition to learn the initialization of the weights, and the biases of all the layers of, say, your ConvNet. You also append to some of the layers, or all layers, a parameter, theta b, and which adds connections that goes into the next layer. And you also learn that parameter vector. And so it's essentially adding other parameters to MAML, other parameters to the meta learning model. They essentially, the argument that they're making is that this sort of decouples some of the gradients that are being backpropagated during learning. This kind of decouples the way that the weights are being updated and the biases are being updated in the meta learner. For more, you should look at the paper. It's called Bias Transformation. I've never tried it myself, but if you have, for some reason, difficulties having success with MAML, that's a thing you should consider doing. And effectively, all it does is that it adds parameters to MAML. Also, what's interesting is that for a single gradient descent step, so here, when we unroll, in practice, we unroll for 5 steps, 10 steps, very few steps, because otherwise the graph becomes too big. You have to backpropagate through too many updates. And so, actually, interestingly, in an iClear paper earlier this year, she showed that a single gradient descent update is enough to make your meta learner a universal approximator of any of these distribution of the label of a new test example given a training step. Which is somewhat surprising. I think we would expect that many updates would be required. She demonstrated that in the context of using the bias transformation and for neural net using ReLU units. Yeah.
Do you have any high-level understanding of the way this works?
No, I don't. I mean, I read it sort of loosely once. Seemed to make sense, but I didn't go into the details. I mean, if someone were to demonstrate that it's wrong, then that would be interesting. But that wasn't. I think it's surprising to some extent, but at the same time, I think the reason this works is that when you're doing this one step of gradient descent and you're fitting that model, you're kind of repurposing some of the parameters of that ConvNet. Some of them will be effectively used to propagate gradients, perhaps, in a nice way for lower layers, and there's still enough expressivity in the full learner, if you allow it to be as big as you want, to potentially even separate like a backprop pathway and a forward prop pathway. So I think the argument ultimately means that if you take something as black boxy as a neural net and you just make it very, very large, you're bound to get some sort of universal approximation. Demonstrating it is not necessarily easy, but in this case, he has arguments for why that is, theoretically. In general, it is true that one-step gradient descent MAML is actually surprisingly effective, but in practice on mini-ImageNet, people use more like 5, and I think often they train for just 5, but actually test with like 20. So again, this is an interesting case of sort of training differently than you actually had a test. And there's a relationship between MAML and doing sort of some form of proper article Bayesian inference. And there's a relationship between a lot of these meta learning approaches and just a Bayesian perspective where you have a prior over effectively models and you're adjusting your procedure for a given training set. In fact, the Josh Tannenbaum paper is effectively like a Bayesian take on meta learning. And so that's something that was published at iClear earlier this year as well. You might want to check out where they draw a more clearer, like direct relationship between the two. And I think I will end with this. And recently on Archive, and that's a submission at iClear 2019, people have tried to sort of investigate various variations of MAML that seems to stabilize learning. So MAML is in general, it takes a lot of memory because your graph actually has multiple copies of the model when you unroll gradient descent steps. So that's one thing that's annoying about it. But another one is, I guess it's something I sort of alluded to. When we compute gradients and we feed that, or when we have these equations that involve the gradient on the parameters, when you're doing meta learning, then you need the gradient of that gradient. So you need second order gradients to train or meta train with MAML. That second order gradient can be expensive to compute if you're not careful. And in general, it will necessarily sort of slow the forward and backward paths of MAML. And so people have used instead the second order version of MAML, which essentially applying a stop gradient on that gradient in the gradient descent recursion in the inner loop of MAML. So essentially just saying that this gradient that you're passing to the mechanism that provides an update, don't actually backdrop through that and stop the gradient. And that sometimes works, sometimes doesn't. It often makes training more unstable. And so in this paper, MAML++, there's a bunch of tricks that they looked at where it seems, according to them, that they're really stabilizing training. So these three curves here are their MAML++, as they call it, for different seeds. And these curves here are the regular sort of presumably first order MAML. That I don't quite remember. It might still be second order, but I think it's first order. And some of the tricks that they use is that if you're doing k steps of gradient descent, at every iteration, you actually have parameters that you can evaluate, is it actually a good candidate for the test set of the episode? You can do that at every step. And so what they suggest is to actually minimize some weighted sum of the performance across all steps. Okay, so instead of, in this figure here, only looking at the loss on the test set of the episode, only at the very end, you actually do it at every time step in the inner loop, every time in theta 1, theta 2, and so on. And doing some sort of weighting, and they even propose some way of having kind of a curriculum where early on you put more weight on the first steps, but then later on more weight on the next steps. They also propose starting with just doing first order MAML, and then eventually actually using the full order version after some number of iterations. So in other words, use first order MAML to kind of initialize regular full order MAML. Actually training the learning rates that is being used. So I mentioned that it's using constant step size learning rate for every step. So it's constant across time steps and it's constant across parameters. They have found that if you have a different learning rate for each time step and a different one for the parameters of each layer, that they get better performance this way. And in this case, they actually do gradient descent also on these learning rates.
So is that like meta learning?
I mean, no, it's just you're adding that. It is still a parameter. So it's not the learning rate on the MAML parameters. It's the inner loop. It's that. It's like it's essentially part of this update mechanism here. So it's a gradient descent step on this guy. Whereas MAML, often this constant step learning rate is often treated as a hyperparameter that you just try various values for. Other things, when you're doing batch norm, instead of using regular batch norm, you actually just assume you always use, even when you're running the training of MAML, you are using the running statistics over the batches, which means you're essentially ignoring some of the gradients that would come from there. And actually also having per time step batch norm parameters. So for every time step, you're going to have a different set of batch norm parameters. That's the gamma and the beta, and training those as well. So this adds just a few parameters, but apparently all of these together sort of allows for more stable training. I don't think this paper has a particularly exhaustive ablation study, at least when I looked at it. So to what extent all of these are necessary, I'm not exactly sure. But I'm mentioning them because, again, if you try to use MAML for some problem, these are good sort of directions to investigate. All right, so I'm already out of time. I won't go over this, but as I said, I'm happy to sort of do a part 2 of this talk. One thing I wanted to quickly mention. Oops. So, and already just with this, like you have a good sense of what are the state-of-the-art methods that people usually compare with. In fact, just today I added some slides of things that people are actively publishing and sending dry clear this year and so on. In terms of the future challenges, I think the directions that are interesting are how to identify the issues that we're finding when we're optimizing on some definition of episodes for training, where maybe we use more ways or less ways or the same. Like clearly we don't quite understand all of that setup. And so, and also I think designing a more realistic, more large-scale benchmark than medium ImageNet, that's something actively we're doing in my group right now, which we're hoping to eventually release, where we actually would have an evaluation procedure that at meta test time, you have different data sets. Or at least within your whole benchmark, you have different data sets from different sources. I think that's a natural next step that, and hopefully I'll be able to share some of that soon. Going beyond just supervised classification, there's a bunch of papers I could point people to maybe in the next part for this talk, but people are looking at meta learning for clustering, for distribution estimation, for structured prediction, segmentation. There's a lot of other applications out there using some of these basic ideas that I talked about today. And ultimately, what I think is interesting is really this interactive setting where a user provides a small training set that they can provide, because it just needs to be small, that you can manually label very quickly some examples, gets a model, and then based on that, maybe corrects it by providing new examples, kind of like the video that I showed earlier. That's not really the setting in which we're investigating these ideas, but I think ultimately that's the setting where we want to be in. And so I think people have looked at things like doing meta-active learning, so suggesting to the user to label certain points and learning how to make that active learning policy, with, I would say, mixed results, like some positive, some less positive. But I think ultimately that would be quite interesting in other directions. And with that, I thank you all. Party organizers. Should I just take the questions offline, or should I take questions here? Yeah. Michael, please come to me.